Okay, we want to look at sums of random variables. This could also be differences, and so if I have a bunch of xi, I equal 1 to n, random variables, and then I let y equal the sum of those, x1 plus x2 plus up to xn. What can we say about the mean and variance of y? And, well, the mean of y is just the mean of x1 plus the mean of x2 plus out to the mean of x3, xn. And that really from the properties of integrals that seems like that's kind of obvious. Now, when I say that, it seems like it's kind of obvious. Well, if I want the mean of y, I want the expected value of y, that is the expected value of the x's, x1 plus x2, or the sum of the x's, xn. But that is, by definition, just we've got an integral here. We've got a bunch of them. So this is 1 to n, a bunch of those integral signs. And we have x1 plus x2 out to xn. And we don't know that these are independent, so we have an f of x1 all the way to xn, so a joint distribution. And then we have our dx1 all the way out to dxn. But these are just sums, so we can break this up into a bunch of separate integrals. So I've got, the integrals with x1 and f, and I'm just going to write f there, and dx1 to dxn plus plus the integrals with xn and f and dx1 to dxn. Okay, so we just have each of those. And if we order our integrals correctly, in every case, this just ends up becoming, the expected value of x1 plus the expected value of x2 for the next one, all the way down to the expected value of xn. So not anything real big there, it just works out nicely. And now when we pair that result with an earlier result on constants, multiplicative constants, if we let z equal the sum of ai xi, like this, so we actually take a linear combination, I equals 1 to n, well then the mean of z is just the sum I equals 1 to n of the ai times the mean of each xi. So that's nice, and that's what you would hope would be the case, is that yeah, we can just add all those separate means together in their linear combination. Now here, there was nothing about independence or anything with that. But now if x1, x2, and so forth, xn, are independent. Now what I mean by that is mutually independent. If they are independent, then our y, we can actually, to get our variance of y, we just take our separate variances of each of the other variables, the xn's. So that's nice. So variances just add. So notice standard deviations don't just add. To get the standard deviation of y, I would need to get the sum of those variances and then take its square root. So it's not quite as nice working with the standard deviation, but not bad. Just work with the variances first. Okay, and then similarly, with the coefficients, if you want the variance of z, where we had those, that's going to be the sum I equals 1 to n of the ai squared, very important, sigma I squared. Okay, but that's very important. So what that says is that if I have y equal x1 minus x2, then the variance of y is equal to the variance of x1, but plus the variance of x2. Okay, so plus, that was a minus, but now it's a plus, because we squared the -1 coefficient. Okay, so that's one that we can get messed up pretty easily. And now, if they're not independent, okay, not independent, it gets very messy with covariances. So if they're not independent and I have a sum, so y equals x1 plus x2 to xn, then unfortunately sigma squared y, so the variance here, is equal to, the sum of the variances, I equals 1 to n of the sigma I squared, but then plus 2 times, and I have to take every single pair of covariances. And so this would be, say, a sum I equals 1 to n minus 1, and I has to be less than j, and then j equals 2 to n. So what this is doing is they're just trying to say I have to get every covariance of every pairing of xi and xj. So you end up with that part, and so it's kind of ugly if they're not independent. All right, well, and I think we'll call that done for that video.